Alright, so continuing on, we're going to look at the z-scores and the empirical rule. So first, let's go ahead and define what the empirical rule, what a z-score is. And a z-score, here's what it looks like as a formula, is any data value minus the mean, divided by the standard deviation. Alright, so remember that that's what all of those symbols mean. The x there is simply your value that you care about. The mu symbol, the Greek symbol mu there, is the mean of your sample, or in this case your population, but we could replace that with x bar. In fact, maybe we'll write the other version here. The other version would be that I have another fraction, and it's x minus x bar divided by s. Right, so there's the version for the population, there's the version for the sample. They really work essentially the same. Now, the idea here also is if we look at this empirical rule and we enlarge this a little bit, we've gone over this before, we've learned that if you move one standard deviation to the left and one standard deviation to the right, that covers 68% of all the data. If you move two standard deviations to the left and two standard deviations to the right, you cover 95. And then if you move three standard deviations and three standard deviations, you cover 99.7. Now, this is, again, where we kind of introduce the idea of that mean minus two standard deviations, mean plus two standard deviations, being your lower and upper fences for those range rules of thumbs, right? Just making sure, I'm pretty sure we covered that. Yep, right here. So you can see from this information right here, and then this chart, right, here's your mean minus 2, here's your mean plus 2, there's your lower and upper fence if you decided to use minus 2 and plus 2, and look what you do, you cover 95% of data within those fences, and if you're outside, then you found something that occurs less than 5% of the time. And if you recall from chapter 1, kind of the introductory section, we kind of in this course lay that kind of the baseline of being significant is being less than 5% of the time occurrence. So that's visually on the normal distribution where that comes from. Now we can again use this formula to calculate z-scores, and what we're going to learn in just a few slides, so to speak, or a few more questions, is that your z-scores will a lot of times not come out to 1, 2, 3, or -1, -2, -3. You're going to end up with a lot of z-scores like 1.835 or something, and we're going to have to learn, well, how do I figure out how much data is in between like 1.835 or something like that? So just keep that in the back of your head, that that's still a mystery we don't have a solution to yet, but it's coming in the future. But for now, the other thing I want to talk about real quick is, for instance, where are these numbers in the middle coming from? Specifically the 13.5 and the 2.35, because we might be a little bit confused on where those come from. So I'm going to do a little bit of work here on the side just to show you, and I'm going to erase it after, but you can see here in the explanation. So hopefully what's pretty clear is that if from the -1 standard deviations to +1 we cover 68, hopefully because of the idea that this graph is symmetric, that if you cover 68% and you cut that down the middle, then you now have 34% to the left and 34% to the right. Now, up next, to get those 13.5s, let's talk about it like this. Moving from, I'm going to write plus or minus 1 standard deviation to plus or minus 2 standard deviations changes our, I'll say density, or I guess I'll say our cumulative data from 68 to 95%. Right? Hopefully that makes sense. We're just kind of reading this rule out loud. If I move from -1 to +1 to -2 to +2, then I've gone from 68% coverage to 95% coverage of my data. Now what that means is we've gained, if you do the math there, 27% of the data, and that must be split on both sides, which makes 13.5% added to each new section. hopefully that's clear there. In fact, I think we will leave that there for you. But that's how we're getting the 13.5 and 13.5. Because when we went from 68% coverage to 95% coverage, that's a total gain of 27%. But it's 27% cut in half over here, 27% cut in half over here. And from there, you could expand that to where do you get the 2.35 from, and so on and so forth. Now, the one key thing we should also say is that if you add all these up, you're going to find that they don't all add up to 100%, because there's still some far off stuff. It's possible to get values that are further than 3 standard deviations away in the positive direction or negative, so just be careful of that. You could get further off the page, but then you would be in that 0.3% chance, which would be ultra rare, so to speak. All right, where are my windows? So from there, let's look at this question, and we'll paste this in on a new slide. And let's see what it says here. Let's make that font a little bit bigger if we can. Okay, so it says the blood platelets have a mean of 261.4 and a standard deviation of 69.4. So that's going to be important. Mean, standard deviation. We could write their true mathematical symbols, but that's okay. And then it says, using the empirical rule, find the following percentages. Now for part A is actually going to be really easy. Here's all part A is. The answer is directly 99.7%. All right. We know that that's the answer because it said within 3 standard deviations, so I don't even need to look at the data. When you tell me exactly how many standard deviations I've moved, I'm just looking directly at this empirical rule right here, and I know plus or minus 3, I kind of memorized 68, 95, 99.7. I already know I've got the right answer there without doing any work because they explicitly told me that I was plus or minus 3 standard deviations. Now for part B, that's the trickier part because we're going to have to calculate some z-scores. So we're going to calculate my first z-score, which is 192, my data value, minus the mean of 261.4, and divided by 69.4. If you work this out, you're going to end up getting, it looks like, negative 59.4 divided by 59.4, which is, of course, negative 1. And so I want to put that on a new line if I can, but it's not letting me. Here, we can do this. All right, so there's the first one. Let's do the second one. The second one's z-score is going to be pretty similar. So I'm going to have a z. It's going to be equal to some fraction. Let's give another new line there. That fraction this time is going to be 330.8 minus the 261.4, and then divided again by the 59.4. And if you work that out, again, you're going to end up with 59.4 over 59.4. I say again, but notice that this time it's positive on top, so we get positive 1. And so look at that. Between both of these two, I know now that my answer is 68% because I just figured out that I was in between minus 1 and plus 1 standard deviations from the mean. And so that's using the z-score to figure out how many standard deviations above or below the mean you are. You take your data value, you compare it to the mean, and then divide that distance by, well, how much distance a standard deviation is worth, so to speak. So that's all we're doing there is we're using this very simple formula, your value minus the mean divided by the standard deviation. Your value minus your sample mean divided by your sample's standard deviation. That will get you a z-score. Now the one thing that I wish was a little bit more well done here is, and we'll write find the z-scores, just to give you a kind of idea there of what we did. And so the one other thing I want to say that's a little bit of a bummer, but I guess it's better for you, is I would have been much more interested if it came out to, hey, one of mine was -1, but the other one was +2. So then you would have been taking the -1, the 34% here, but then for +2, you take this 34 and the 13.5, and you'd really need to know how to know those sections rather than just, memorizing those top numbers, so to speak. So, what I think is a less interesting question is your E's in the course. So there you go. Well, let's answer it and get the credit. Why not? We did the work. And there we go. I think at that point, yep, that gets us through. But we just introduced the idea of z-scores. So now let's move on and look at 3.3. Where'd it go? There we go. All right. Sorry, as I'm looking through, I'm not sure the video's capturing my changing around of stuff here. So give me a second. Just to make sure that that stays there. All right. So this first question here is really a vocab question, and sorry, we should do that over here. Just underneath, we should say a z-score tells you how many, I'll adjust this and make it look nice in a second, standard deviations a certain value is from the mean. Alright, change our font size, make that a little smaller. Great. Move this a little bit below. Alright, just some formatting there, sorry about that. That's all a z-score is doing, is it's literally telling you how many standard deviations away you are from the mean. And so, if we again look at that question from the homework real quick, it says, hey, there's a z-score of 4.10, and then it says, how many standard deviations are you above the mean? Well, they literally just self-defined, so it's a trick question, so to speak. All right, up next, let's see what more we can do with this. Up next, we kind of move on to box plots for a little bit. And this question is kind of a wacky one, but let's look at it. It essentially says that the box plot shows waiting times for two different lines. Which would you prefer? Or does it not make a difference? Explain. Now, this one, again, I'm kind of going to let the answer slip for you, but because I don't necessarily agree, because you might have a higher risk tolerance or a lower risk tolerance. Let's see what we mean by that. When I look at this, and I look at these, what we call box and whisker plots, and so maybe we should define those real quick. A box and whisker plot is we're going to say graphical representation of the 5-number summary. We've not looked at the 5-number summary. Let's talk about what it is. It's the min, it's the Q1, the median, the third quartile, and the max. Now we haven't actually defined the Q1 and the Q3, so let's do that really quick. Insert a few text boxes here. Hopefully we know what the minimum is. That should be fairly straightforward. Oops. But let's see here. For the Q1, I'm going to write it like this. The boundary line of the bottom 25% to the top 75%. All right, that's what the Q1 is. Similarly, we've done this before, we should know what the median is. It's the separation between the bottom 50% of data and the top 50% of data. And you guessed it, the third quartile is then what separates the bottom 75 percentiles from the top 25 percentiles. Those are what your quartiles are doing. They're separating, well, the quarters, right? 25, 75, those sounds like, I had 1 quarter and 3 quarters. I had 3 quarters and 1 quarter. I had 2 quarters and 2 quarters. We're talking about the quarters, or 25%, groupings of my data. Now, from there, what we can do is we can say the Q1 median and Q3 are represented as vertical bars and connected horizontally to form a rectangle. From the rectangle, we draw single lines or whiskers to the min and max. All right. So after that, we now can go back to this homework question and understand what we're being asked here when we look. And maybe we can even snip these out. Awesome. Okay. So we now have this box and whisker plot here. I know those numbers are a little small, but here's the idea. You're going to wait in one of these two lines. Now here's my argument, which again coincides with the homework's argument, but maybe it's phrased a little bit differently. The idea here is, what this is saying is, in this first line that you're waiting in, 25% of the time you'll wait from 22 to 23 minutes. 25% of the time you'll wait from 23 to 24 minutes. 25% of the time you'll wait from 24 to 25 minutes, and 25% of the time you'll wait from 25 to 26 minutes. So we have, right, essentially almost all the data is between 22 and 26 minutes, and all of those quartiles are actually equally spaced numerically, and you can even see right below that is not always the case. Below, 25% of the time you'll wait 17 to 22 minutes. Now that sounds good, but let's keep going and think about it. Up next, I could 25% of the time wait from 22 to 24 minutes. Essentially, this 25% of the data was the entire 50% of the data up here, if you're kind of thinking about it in that way. Up next, another 25% chunk is from 24 to 26 minutes, and from there, 26 to 31 is another chunk. Now, you might also be weirded out by saying, wait a minute, how can there be 50% of the data in this small chunk over here, but outside over here there's not nearly as much data? And that's where I would say, well, although this is not probably representative of a normal distribution, think about the normal distribution. There is a bigger chunk of data in the middle. 68% of the data is right here from -1 to +1. And as you fan out, you have way less and way less data. So the further away you get, the less data you cover. And so, in other words, you can have these further wings that it takes to get a collective 25%, if you think about it that way. So again, over here, these wide wings mean that there's very few data points here, I guess spread out, or I guess not very few, 25% of the data points, but they're more spread out across this range compared to here. They're much more tightly close together. Now, when it comes to which line you would want to wait in, all right, that's the crux of the question. I think I would want to wait in the top line to have much less variation, so that fewer customers have to wait a significantly long time. I think I'm going to go with that wording. In fact, I'm almost curious to see if this question allows multiple ones, but let's see what we mean here. I know for a fact that if I wait in this top line, yes, I might not get the 17 to 22 minutes, but think about it for the bottom group. The bottom group, only 25% of the time that would happen. The majority of the time, or 75% of the time, you would wait 22 to 26 minutes, or even take up to 31 minutes. I think I'd rather value the consistency, so to speak. I'd rather have the closeness together of saying, I know it would, in the best case, be 22, in the worst be 26. Yeah, I won't get the 17 if I got lucky, so to speak, but I wouldn't get the 31 if I was unlucky. So I think I would take the top. there's less variation. In other words, literally the graph is closer together. And so there's a less potential that I would wait a long time. All right. In fact, I'm just curious. I want to go through it. Maybe I say I want to go through the bottom because there's much more variation. So, well, no, more customers don't wait. Yeah, no, I think that's just the one right wording now that I look back at it a second time. All right. Up next, I'm going to let you reason through that question. Let's take a look at this one. We're kind of introducing box and whisker plots, and then we're kind of going back through interchanging which one we're going to use. So up first, if we look at this question, really what we're being asked to do is kind of deconstruct the z-score formula one part at a time. Whoops. So let's see what I mean by that. All right. So for this equation, sorry it has that question viewer there. Let's see here. We have a mean of 17.05. Notice it's using x bar this time, but that's fine. Standard deviation is 32.73. And then they say, hey, look at this data value. There's a 72.5, which was the highest. And essentially, they're at some point wanting the z-score, but we need to break it into parts. So part A is literally just saying, hey, can you go ahead and take the 72.5 and compare it to the 17.05 mean? And so let me do that in my calculator real quick. All right, and doing that, I got 55.45. From part B, then it says, how many standard deviations are you from or how many standard deviations is that being the result from part A. Now, in other words, again, just to point out here, all they did was they just broke down a z-score. They first took your 72.5, they then compared it against the average, 17.05, and they just wanted you to work out that numerator first, so to speak, if you can see that. On the bottom, they want you to divide that by the 32.73. And so again, let me use my calculator to do that. 32.73 dividing. I get 694, which I guess I'll go to 2 decimal places. And then it says, if we consider speeds of -2 and 2 to be significantly low or high, is the carrier's highest speed significant? We can go to the homework and answer that. Again, we got 1.69 standard deviations. And is that significantly high? Well, again, the z-score is 1.69 because it's the same thing. And it's not significant because it sits within those fences, as we've discussed that idea before. Up next, we're actually back to using the range rule of thumb, which is, again, take your mean and do -2 standard deviations plus 2 standard deviations. We'll skip over that because we've already covered it. Up next, let's look at this one. We'll do some comparisons of z-scores. And that's actually the whole point of what we're doing here, is we want to get to a point where we can compare our z-scores. Right? And so sometimes when you do your z-scores, it's nice to, write subscripts to kind of see where you were getting your answers from. So it says the tallest man had a height of 259 centimeters. Reading a little bit further, kind of going maybe out of order, but in order as the question states it. The shortest man had a height of 210.8 centimeters. And now it says, hey, did you know that there is a mean height of 176.17? Well, guess what? No matter what you're doing, you're still going to subtract the mean, so they're both going to get that subtraction. And then they're both going to be divided by the standard deviation of 8.11 and 8.11. Now, if you work this out, let me do that real quick. Alright, so some slight rearranging of the windows, but what we end up getting is, after we calculate both z-scores, that the tallest man has a z-score of 10.21 and the shortest man has a z-score of -0.86. Now the question is, which of these two men had the height that was more extreme? Well, extreme is measured by the z-score, and more specifically by the absolute value of the z-score. So we'll say since 10.21 is further from 0 than negative 8.06, the tallest man has a more extreme height. Right? It's not more extreme because he's taller, right? Don't get those confused that more means like more than or greater than. In this case, it's the absolute value that we're talking about here. Both are extreme. Both are significantly far away from the mean, the norm. It's one is further more extreme in the taller direction, and one is less further away in the extremity of the shorter direction or the negative direction. But if this was negative 11.06, then now it would be the shortest man who has the more extreme height, because negative 11 would beat out 10. Right? It's about the absolute value of those scores, which is why I say further from 0. All right? So there we go. That's how you compare z-scores. You compare them by their, z-score values, and you absolute value them, and you consider them that way, not just based off their numbers. Okay, I think at that point, let's see here. We've got another one that's about the same. You're going to do some more z-score comparisons, so you can handle that on your own. Percentiles will let you discover that on your own. And now let's settle into the box and whisker plots, and I need to go ahead and answer this at random because I already started it. And we'll go back and we'll take a look at some box and whisker plots. Okay, so from this point, let me make sure it's going to actually display the questions here. From this point, we're dealing with those box and whisker plots, and we're talking about the 5-number summary. Now, the good news is we've gotten used to using this menu a lot. We can go ahead and open this in StatCrunch. And once we open this in StatCrunch, we can simply say that we want the summary statistics, right? It's called the 5-number summary statistics. And we're going to do that on the column because our entire data was put into a column, and var1. And we don't have to choose any special stuff because there's the min, max, Q1, Q3, and median. It's a little bit written out of order, but they do want it in order. So let me arrange my windows so I can see them and write them. The min is 1, the Q1 is 4, the median is 5, the Q3 is 6.5, and the max is 9.5. So there's my 5-number summary. From there, they want me to pick the box plot that corresponds to that. And so just be careful that you read those numbers. 1 should be at the end, and it looks like it's at the end. Oh, not for D. So we know that D can't be right because it has the wrong minimum. From there, the first part of the rectangle should be at positive 4. And so that's not going to be true for A. That's not going to be true for B as well. So based on those two, the min not being at 1 here, and the Q1 not starting at 4 for A and B, I've eliminated my choices and figured out that C is correct. And you can even see that between 9 and 10, right, that's where they stop this whisker. I know that's kind of small to see here, but you'll see it on your homework. Or wait, never mind. We can hit the plus button or open this in its own window. So there's the 1. There's the 9.5. It's between 9 and 10. So they're drawing it accurately. All right. And so the good news is you can see here that if you have to make a 5-number summary, well, you can again just open in StatCrunch and find the min, the Q1, the median, the Q3, and the max. If we had to do this by hand, that would be a lot harder. We'd have to first rewrite all these and sort them. We'd have to make sure we cut in half and then cut those halves in halves to get the quartiles. It would not be a fun time. We've got more find the box plots here, and we've got the data sets for men and women. So maybe let's look at this. And we can open this in StatCrunch. And we can go ahead and say that we want, again, the summary stats. But this time I'm going to shift and select both of them. And maybe what I'll also do is I'll shift and select, or control or command select, to just get the values that I want. and nothing more. All right. So at this point, I've got everything I need. And let's just see how they ask these. They first say which one would correspond to the men's data. And so I'm looking for a min of 50. That's not a min at 50, so A is out. B is in. C is out because that's not at 50. And D is in. So far we're down to just B and D just by calculating the min. From there, it looks like what's going to be the thing between these two is where is that median, right? This one's median looks like it's a bit over 70. This one's median looks like it's a bit under 70. That's the next kind of thing I can really quickly notice myself as I look at it. So which one for the men shows a mean below 70, 66.5, right? Don't be confused here on StatCrunch. We're just reading that top section because we're only caring about the men. So I wanted the min of 50. I want the median of 66.5. D shows a median below 70 at 66.5. The other one was above. So again, because the min was at 50 for B and D, and because the median was correctly at 66.5, I can be assured that the rest is correct through process of elimination. Then they want me to do the same thing for the women. The min is 58 this time, so it looks like B is correct and D is correct. It looks like C and... actually, it looks like A still might be right. That looks like about 58. Now let's look at the... it looks like what's going to be next most beneficial is maybe looking at the first quartile. So for the women, the first quartile starts at 70. A has that. B has that. But D does not have a first quartile at 70, so it looks like we're down to A and B. And it looks like the median will cover this for me. The median for the women is 76. And careful, the median here, the middle line in the rectangle is at 80. So it can't be A, it must be B. That one was at 76. Again, I know that's small, but you can zoom out and see that better for yourself. Up next, I do want to read through and give this comparison one, and we might be able to get away with it by just reading these number summaries right here rather than reading out the actual charts. So, in general, it appears that men have higher pulse rates than women. Let's see if we can verify that. The median for men is actually less, so automatically that's going to kind of pull that out from being true. And actually, I guess it's kind of nice that B and D are stacked right here. You can see that the men's pulse rates, I would say, appear to be less because their interquartile range actually stops at around, 75, and the women's is just starting to hit the median at around 75, So, not A. It appears that men have lower pulse rates, and do we think that the variation is similar to women? Let's see here. Variation, one thing we could say there is, I think their interquartile ranges are pretty similar. And we go from, let's see here, essentially 58, well, we can see it here. From 58 to 104, that's about a distance of 50. This is a difference of 40. So I would say the men's pulse rates have less variation, or maybe similar. But let's see here. Men have lower pulse rates and men is much greater. So it's definitely not much greater. We know it's less variation we can see from the min and max. So I guess we're going with similar in this case. All right. And then we get some review questions. But really your box plots are just your 5-number summary here. So your min, your Q1, median, Q3, and max. And again, the good news is that your StatCrunch tools give all of that for you for free. So that's the remainder of Chapter 3, and we actually already covered 4 in an earlier video, but depending on the order you're watching it in. Anywho, we're now done with everything from Exam 1 material, at least in the order I recorded it. I'll see you all for whatever section we cover next.